Hi guys, in the previous lecture we have covered single phase half wave control rectifier for RE and RLE type of load. Means in all the previous lecture we have covered single phase half wave rectifier. So in this lecture we will solve some problem based on half wave rectifier that has been asked in GATE exam from 1991 to 2017. We will solve all the problem related to single phase half wave rectifier that has been asked in previous year GATE exam. Okay, so there are total of 11 question that has been asked in previous year GATE exam that we are going to see. Okay, so let us proceed to the first problem. In all the problem I will be giving you the reference of lecture in which the concept has been discussed. So before watching this lecture you should revise all the lectures that is related to single phase half wave rectifier, that is lecture number 9 and lecture number 10. That is, there are total of 6 lecture related to single phase half wave rectifier. You should watch or you should revise the concept that has been discussed previously, then proceed to this lecture, that is the lecture number 11. And in all the lecture I will be giving you the reference in which the concept has been discussed. So let us move to the first question. This has been asked in GATE 1994. Referring to the figure, the type of the load is, see, this is the single phase half wave controlled rectifier, right? And we have to find the load by seeing the output waveform. This is the output waveform and this is the source supply voltage. So supply voltage is sinusoidal and we are getting output voltage like this. Okay, so you can see my lecture number 10C where the output voltage I am getting like this. So this is the RLE type of load. I have already discussed in lecture number 10C. So RLE type of load is nothing but DC motor load. So option C is correct. Now see the next problem. A half wave thyristor converter supplies a purely inductive load as shown in figure. If the triggering angle of thyristor is 120 degree, means alpha is given as 120 degree and we have to find the extension angle. So beta will be what? This has been asked in GATE 2001 and the concept has been discussed in lecture number 10B. So if you have watched my lecture number 10B, that is the single phase half wave uncontrolled rectifier for L type of load. So there I derive the beta. Beta is coming out to be 2 pi minus alpha, that is equal to 360 minus 120, that is equal to 240 degree. So extension angle will come out to be 240 degree, that is option A is correct. See the next problem. A single phase half wave controlled rectifier is driving separately excited DC motor. Let us see, this is single phase half wave controlled rectifier. Okay, and it is driving the DC motor. So DC motor will look like this. The DC motor has a back EMF constant. Back EMF constant is denoted as KB, that is given by 0.5 volt per RPM. The armature current is 5 ampere. This is 5 ampere armature current without any ripple. Armature resistance is 2 ohm. Here the armature resistance is 2 ohm. The converter is working from 230 volt. Source voltage is given as 230 volt RMS. Single phase AC source with a firing angle of alpha is given as 30 degree. Under this operating condition, we have to find the speed of the motor. So we know that E is equal to K phi N. We know this. So for constant flux, we can write E is equal to KBN, where KB is given as the back EMF constant, that is equal to 0.5 into N. So N will come out to be E upon 0.5. So if I will find the back EMF, then we can easily get the speed. Now to find the back EMF, we have to see the terminal voltage of DC separately excited DC motor, that is V0. So for RLE type of load, V0 will come out to be Vm upon 2 pi into 1 plus cos alpha. See my lecture number 10B, you will understand this, that output voltage is coming out to be Vm upon 2 pi into 1 plus cos alpha, that is equal to, put alpha is equal to 30, you will get 230 root 2 upon 2 pi into 1 plus cos 30, that is equal to 96.6 volt. Now we found output voltage V0. Now this V0 is the terminal voltage for this DC motor. So V0 I can write that is equal to I0 into RA plus E, where E is will lie somehow here. So E I will get that is equal to V naught minus I naught into RA, where I naught is given 96.6 minus I naught is given 5 into 2, that is 10. So E will come out to be 86.6 volt. Now you can easily find the value of N. You will get E by 0.5, that is equal to 86.6 by 0.5, that is equal to 173.2 rpm. Okay. Now see the next question. A single phase half wave uncontrolled converter circuit shown in figure like this. A two winding transformer is used at the input for isolation, assuming the load current to be constant. Here the I naught is constant, hence load current is continuous, and V is equal to Vm sin omega t. Input is AC. The current waveform through diode D2. We have to find the current waveform through diode D2. So we can find the conduction angle of diode D2. See, this is the load current that is continuous, okay, and let us suppose this is pi and this is 2 pi. So from 0 to pi this supply voltage is positive, so this D1 will conduct, and after pi this D2 will free wheels. So from pi to 2 pi I will get conduction in D2. Is it fine? So after pi, this diode, freewheeling diode will starts conducting, and since load current is constant, so it will continue to conduct till D1 is not conducting. Means after 2 pi again supply voltage will be positive. So this D1 will start conducting and D2 will be off. That is option D is correct. This concept has been discussed in lecture number 9b. Go through that, you will understand. Now see the next question. A single phase 230 volt 50 Hz AC main fed a step down transformer. This is something like this. A step down transformer. The ratio is 4:1. Okay. And here the input supply is 230 volt 50 Hz. Supplying power to the half wave uncontrolled. Half wave uncontrolled will be like this. AC to DC converter used for charging battery, means charging battery means RE type of load, okay, where EMF is given as 12 volt with the series current limiting resistor R is equal to 19.04 ohm, and we have to find the charging current that is equal to I naught average. So this concept has been discussed in lecture number 9C, that is single phase half wave uncontrolled rectifier with RE type of load. So in that lecture I have derived the charging current equation, that is equal to I naught average is equal to 1 upon 2 pi r into 2 Vm cos theta minus E into pi minus 2 theta. Go through that lecture, you will understand how the I naught average I am getting like this. So put the value of R, put the value of Vm. Vm is equal to, see, Vm is nothing but here, Vm is the secondary maximum voltage, so I can easily find. So secondary voltage Vs will come out to be 230 by 4. See here, 230 and ratio is of transformer is 4:1. So secondary RMS voltage, that is equal to 230 by 4, that is equal to 57.5 volt. Now this is the RMS voltage. Here I have to find the Vm. So Vm will come out to be RMS multiplied by root 2, that is equal to 57.5 root 2. Vm will come out to be 57.5 root 2. Okay. R is given, that is equal to 19.04. E is given 12 volt. Now you have to find the theta angle. So for finding the theta, I have already explained you theta you can find, that is equal to sin inverse E by Vm. From where I am getting the sin inverse E by M? What is theta? Theta is the angle at which supply voltage is equal to E. See the waveform of RE type of load. The theta is the angle at which supply voltage is equal to E. Supply voltage is Vm sin theta, that is equal to E. So theta will come out to be sin inverse E by Vm, where E is equal to 12 volt and Vm is equal to 57.5 into root 2. Okay, so in this way you can calculate theta. Now theta you will get 8.486 in degree. So in radian you have to calculate. In radian what will be the angle, the theta? The theta will be 8.486 into pi by 180, that is equal to 0.148. So put theta in radian here, okay, and theta in degree here. Vm is equal to 57.5 root 2. You will get I naught average, that is equal to 1.1 ampere, means it is approximately equal to 1 ampere, that is option D is correct. Okay. Now let us move to the sixth question. In the circuit of adjacent figure, the diode connects the AC source to a purely inductive load. The purely inductive load means this is single phase half wave uncontrolled rectifier for L load, and the concept has been discussed in lecture number 9a. The diode conducts for, we have to find the conduction angle of diode. So conduction angle of diode is nothing but, in single phase half wave uncontrolled rectifier for L load is 2 pi. So conduction angle of diode is coming out to be 360 degree, that is option D is correct. Now let us move to the seventh problem. In this problem, the circuit is given, AC supply is given and it is connected with diode and purely inductive load, means this is also single phase half wave uncontrolled rectifier for purely L load, means this concept has been discussed in lecture number 9a, and we have to find the current waveform through the inductor. So current waveform through the inductor we have already seen in lecture number 9a. This is Vm sin omega t, and current I was getting something like this up to 2 pi, and the maximum current I was getting at pi, and the current equation that is equal to Vm upon omega L into 1 plus cos omega t. Is it fine? Go through lecture number 9a, you will understand from where this current equation I am getting. Okay, this is Imax. Now see here, input frequency is 50 hertz. This is the input frequency is 50 hertz, and output current frequency I am getting like this. So what will be the time period? This time period will be 1 upon 50, that is equal to 20 millisecond. Input frequency is 50 hertz, means up to 2 pi, the time period will come out to be 20 millisecond. So this is the current equation waveform, total waveform will come out to be 20 millisecond. See here, only option C is matching. See, the current equation I am getting like this, and it is up to 0 to 20, that is this is 20 millisecond. So option C is correct. Now you can find the maximum current also. Maximum current I was getting at omega t is equal to pi. So at omega t is equal to pi, the maximum current will be, sorry, this will be in minus. The IT will be Vm upon omega L into 1 minus cos omega t. Now put omega t is equal to pi in order to get the maximum current. You will get maximum current is equal to 2 Vm upon omega L. Put omega is equal to 100 pi, L is equal to 0.1 upon pi, and Vm is equal to 10. You will get that is equal to 2 ampere. So maximum current I was getting 2 ampere. So option C is correct. You can go through these two options, means either find the maximum current or find the time period. So time period of this current waveform I am getting from 0 to 2 pi, that is equal to 20 millisecond. Okay, see the next question. Thyristor T in the figure shown initially off, and it is triggered with a single pulse width of 10 microsecond, means this thyristor is triggered. It is given that L is equal to this much and C is equal to this much. Assuming latching current and holding current of the thyristor is 0, means what do you mean by this? This means this is triggered at T is equal to 0 only. So this is nothing but diode circuit. Is it fine? Now this diode LC circuit I have explained in lecture number 6b, and I have to find the T conducts for, me this thyristor will conduct for. So in order to find the conduction angle of thyristor, the current equation that is equal to, I was getting Vs under root C by L sin omega naught T, and this current I was getting up to pi. If you have watched my lecture number 6b, then you can understand this current I was getting up to pi. After pi, the current is going to be negative, so this thyristor won't allow the negative current. So I am getting current up to pi. So put this equation is equal to 0, then you will get the conduction angle of thyristor. So omega naught T will come out to be pi. So T will come out to be pi by omega naught, that is equal to pi under root LC. So put the value of L and C, you will get pi under root 100 by pi into 100 by pi, that is equal to 100 microsecond. So option C is correct. Now let us move to the next question. The figure shows the circuit diagram of rectifier. This is single phase half wave controlled rectifier with freewheeling diode, means this is RL with freewheeling diode. Okay, having R is equal to 10 ohm and L is equal to 0.505 Henry. Okay, connected in series. Assuming ideal thyristor and ideal diode, the thyristor firing angle needed to obtain an average load voltage of 70 volt. We have to find at what angle, at what triggering angle the output voltage will be equal to 70 volt. So output voltage in case of RL with freewheeling diode, I was getting that is equal to Vm upon 2 pi into 1 plus cos alpha, and this is equal to 70 volt. Vm is nothing but 325 upon pi into 1 plus cos alpha is equal to 75. So alpha will come out to be 69.31 degree. This concept has been discussed in lecture number 10b. Go through that lecture to understand the concept. Now see the next problem. A diode circuit feeds an ideal inductor as shown in the figure. Given Vs is equal to this much, where omega is this and value of L is given. The initial value of inductor current is 0. Switch is closed at t is equal to 2.5 millisecond. Then the peak value of inductor IL. What is the peak value of inductor? See here. If this switch was closed at t is equal to 0, then this will behave like a single phase half wave uncontrolled rectifier with purely L load. If this switch was closed at t is equal to 0, then, but here this switch was closed at t is equal to 2.5 millisecond. So let us plot the input voltage that is equal to Vm sin omega t like this. Okay, and I am closing the switch at t is equal to 2.5 millisecond. So first I have to find the theta angle, the angle corresponding to this 2.5 millisecond. See, the time period is, this is 50 hertz na, input supply frequency is 2 pi f, that is equal to 50 hertz. So time period is 20 millisecond. So 20 millisecond correspond to 2 pi, or you can say that correspond to 360 degree. Okay, so 2.5 millisecond will correspond to 360 by 20 into 2.5. Is it fine? So angle will come out to be 45 degree. What do you mean by this? Means this switch was closed at an angle of 45 degree. Okay, after that you will get the current. So I can replace this whole switch with diode by thyristor. I can say that this whole combination is nothing but thyristor, and it is triggered at an angle of 45 degree. Is it fine? So this is nothing but single phase half wave controlled rectifier with L load. I am replacing this switch and diode with thyristor because this switch was closed at t is equal to 2.5 millisecond, that is equal to at an angle 45 degree. Okay, so at an angle 45 degree, so I can write like this, alpha is equal to 45 degree, and I can do the operation. And in this case the current equation I was getting like this, Vm upon omega L into cos alpha minus cos omega t, and current I was getting like this. The maximum current I was getting at pi, and this is 45, and extension angle is equal to 2 pi minus 45, that is equal to 315 degree. Okay, now you have to find the peak value of inductor current. The peak value of inductor current I am getting at pi. Okay, so put omega t is equal to pi and alpha is equal to 45 in this current equation, and Vm is already given, that is equal to, I think this is 100. Okay, so I max I will get, that is equal to 100 by omega is 100 pi. You will get IL max, that is equal to 17.07. Now let us see the last question that has been asked in GATE 2017 set 2 for 2 marks problem. In the circuit shown in the figure, the diode used is ideal, and you have to find the input power factor. So this concept has been discussed in lecture number 9a. This is single phase half wave uncontrolled rectifier with R load. Okay, so to find the input power factor, I have already explained you have to put the P in is equal to P out. Okay, and P in is nothing but source RMS voltage, source RMS current into cos phi is equal to P out. Since this is voltage stiff type of load, so output power I will get, that is equal to I RMS square into R. Okay, so cos phi will come out to be, since this is R type of load without freewheeling diode, so output RMS current and source RMS current are equal, that I have already explained you in lecture number 9a. So I will get IOR into R upon Vs. So I can write like this, RMS output voltage upon Vs. Hence cos phi will be, what is the RMS output voltage of this rectifier? RMS output voltage is Vm by 2, while RMS source voltage can be written as Vm by root 2. So solve this, Vm will cancel out, you will get 1 by root 2, that is equal to 0.7. So input power factor is coming out to be 0.7. This has been asked in GATE 2017 and the concept has been discussed in lecture number 9a. So this much problem has been asked in the previous year GATE exam, and all the concept I covered in my previous lecture, that is lecture number 9 and lecture number 10, related to single phase half wave rectifier. So whatever I am delivering you in my power electronics lecture, that is sufficient for cracking GATE exam. All the concept I am including in my lecture, so you don't have to worry about power electronics. Whatever the concept I am delivering you, that is sufficient for cracking GATE exam. So follow the power electronics lecture. Also subscribe to this channel for more updates. So that's all about this lecture. In the next lecture we will see single phase full wave controlled rectifier. See, I am skipping uncontrolled rectifier because all the formula that I will derive in controlled rectifier, you have to just put alpha is equal to 0, you will get the parameter related to uncontrolled rectifier. So if you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving, you can join our Facebook group. Thanks for watching this video.